Yeah.
Stand in the middle of the
Oh, okay. It is my very pleasure to introduce Professor Gary Ferland from the University of Kentucky. He made the very famous code, ionization code cloudy. I personally use it heavily every day. Uh, he got his bachelor's and PhD from University of Texas in 1978. And then he did his postdoc in Cambridge from 1978 to 1980. And then he became associate professor in the University of Kentucky right afterwards. He got tenured in OSU and then moved back to Kentucky, University of Kentucky in 1992. Um, please welcome him.
Okay. Thank you very much, and thank you for coming to my talk. So I'm going to talk about cool core cluster environments and these filaments that came around it. So this is the Perseus cluster, a famous image by Consolisi and shown in H alpha. And this is something out there in the sky that first attracted attention in the 1940s when first deep optical plates were taken of the brightest cluster galaxy in one of the nearest and brightest cool core clusters. And so there are many, many fascinating problems in this environment. So I consider myself primarily a spectroscopist. That's something that not too many people do anymore. And I'm mainly involved in understanding how matter makes light. Here we go. And just as an aside, I want to show why this is hard. This is very, very hard because if you're dealing with light, you're dealing with the many-body Schrodinger equation when you get started. And then you get past that bad boy, then you got to move on to multidimensional radiative transfer. And that has its own challenges. And so making progress in this field, understanding how matter and light how matter makes light and how matter absorbs light, has a series of very, very, very messy problems because of the messiness of the many-body Schrodinger equation. So move on. Not quite, there we go. My partners in crime in this, my co-conspirators, are old friends. Andy Fabian is here on the right. This was during the 50th anniversary of the IOA, Institute of Astronomy, Cambridge, last summer. So Andy Fabian and I were brand new postdocs at the Institute of Astronomy in the late 70s. And we cowered in fear of this mighty university around us. And Roderick Johnston, a long time collaborator and friend, is here in the center. So this was the Roderick and Andy were the colonel of the X-ray group at Cambridge for quite some time. So Andy began working on clusters of galaxies about the same time my job at Cambridge was to work on quasars. So just to back up to clusters of galaxies for a second, this is a map of the entire quadrant of the sky. If you could look up at the sky with a pair of binoculars, you would see this string of galaxies, the Perseus supercluster, Perseus Pisces supercluster. Then up over here is the Perseus cluster of galaxies. And the Perseus cluster was one of the objects Franz Zwicky looked at back in the 1930s when he first realized that there must be dark matter holding together clusters of galaxies. This is one of it's a good piece of the sky and it's fun to look at in binoculars. And in the center of this cluster of galaxies is the brightest cluster galaxy, the brightest one in the center. You can understand why the galaxy in the very center of a large cluster might be the very biggest one. So that's in the very center of a huge gravitational potential well, so the material would go down there. This is NGC 1275, the brightest cluster galaxy, the BCG, And it's one of Carl Seifert's original Seifert galaxies. You can see it has this brilliant star-like nucleus in the very center. You can also see an infalling absorption system from optical spectroscopy. You can tell there's something falling into the galaxy cluster towards 1275. It used to be thought this was a galaxy nearly able to merge with 1275. It's now thought that this infalling system is out near the outskirts of the galaxy cluster. But this absorption here, mass condensation, and then the star-like nucleus, the signature of a supermassive black hole. When the first X-ray missions were launched, their attention was drawn to these clusters of galaxies. These are some of the brightest things in the X-ray universe. So this is a Palomar sky survey superimposed with an early X-ray image showing that there's very, very powerful extended X-ray emission going down towards the brightest cluster galaxy. This is a modern view of the night sky taken in the X-rays. So you see a lot of X-ray sources, but then you see these extended sources, which are other galaxy clusters. So the X-ray sky reveals many of these environments across the cosmos. When the first work was done in the early 1980s on the hot gas in clusters of galaxies, they were termed cooling flows. And the reason for that is the hot gas has temperatures of several million degrees Kelvin, and you can figure out simply from the observed X-ray flux and that temperature how long that gas would exist. If you think about the total mass you're looking at, you can figure out the thermal energy. And if you look at the power coming out, how long would it take to radiate away that thermal energy? And it turned out that time scale was much shorter than the Hubble time. And so the model that was developed, the cooling flow scenario, was that the hot gas was cooling off and then collapsing towards the center to form stars. And so this was the general idea until the X-ray spectroscopy was reborn with Chandra XMM. And so they were able to get really good spectra of the X-ray emission, and it was discovered that they did not detect the cooler X-ray emitting gas that was expected if this really was a cooling flow. So the initial scenario, you start out with a big bubble of very, very hot gas. You can figure out easily how long that would take to cool off. It has no energy source by postulation, and so there's a time scale for it to cool off shorter than the Hubble time. So it should collapse and form stars. And as it collapses and cools off, it should go through all the gas phases, should 10 to the 6, 10 to the 5, 10 to the 4, 10 to the 3, down to 100 and form a molecular cloud that would make a lot of stars. The cooler gas was not seen, and the cooling flow idea became the cool core cluster idea. So there had to be something that was gently reheating the hot gas in this cluster. And so the observation taken at face value said that the hot gas would start to cool, then it would get down to about 1/2 or 1/3 of its original temperature, and then some gentle heating process would heat it back up. The problem with that scenario is it's hard to figure out. It's a fine-tuning problem. The analogy that's often made is we have the temperature, the surface of the Earth, a very comfortable 20 degrees Fahrenheit. If it were an empty space, it'd be down 2.7 degrees Fahrenheit. So we want to warm up the surface of the temperature to a gentle, livable temperature. And all you have to do this is H-bombs. So the problem here is you have a big black hole in the center. The big black hole makes jets. It makes a lot of activity, very, very energetic activity. That's the main energy source you can think of. So how can you use big black holes to gently heat up the entire cluster environment to about 1/3 of where it started out? if you look down at the center of the Perseus cluster, so this is one of Andy Fabian's favorite. He's very, very good at visualizing data. So he's turned this into a kind of a Halloween pumpkin. You can see that the X-ray, this is a hot X-ray gas, and you can see that it's been punctuated by various things, and active galaxies have lots of jets coming out. There's lots of evidence of some kind of jet hot gas interaction. And so that's the tools you have to heat up the gas with a black hole, the jets it makes, and other kinds of sound waves that might punch out into the intergalactic medium. Andy reused that image, an astronomy picture of the day, is the Halloween image for, I think, 1978, so some time ago. So it's a grinning skull from the Perseus cluster looking back at us. So it's not by no means homogeneous, it's getting stirred up. There are other images that show that the X-ray gas, the very, very hot gas, is being disturbed in various ways. This is a different cluster environment, but one where you can see that the hot plasma making the X-ray emission is out here in a shell, and then there's synchrotron emission from the black hole with its jets, so something like a pulsar wind nebula down here in the center. So those are the energy sources we have to work with in this environment. So as I go along, what I'm going to jump into some spectroscopy questions, but if there's any questions, please feel free to ask as we go along. There's the infalling system in Perseus. There's the radiosynchrotron source in Perseus, the quasar in the very, very center of this galaxy. So those are the basic ingredients are going to be this very, very hot gas that should be cooling off. And then we have this powerhouse down in the very center. And we need to stop the cluster environment from cooling down below about a third of its initial temperature from the X-ray emission that we see. This is not Perseus. This is, the name is unreadable in the corner, but this is another poster child for watching black hole jet interactions with X-ray gas. So the red is synchrotron emission. It's the brightest cluster galaxy in the center, baby quasar making its jets. And then here is the hot gas surrounding it, making the X-ray emissions. So there's clearly an interaction between the black hole and its jets and the surrounding hot gas. But what it's done, it looks like it's kind of sucker punched its way right through the hot gas and blew its way through. And it's hard to imagine how this is going to gently heat the entire hot gas to be consistently a third or a half of its initial temperature. So that's the scenario with what's now been termed the cool core cluster phenomenon. The last ingredient here, which is also the image that opened the very first slide that opened the talk, is what surrounds the brightest cluster galaxy, what surrounds NGC 1275. So there's a network of tenuous, very beautiful, almost diaphanous looking tentacles lingering around the galaxy itself. So this image is by Consolisi and shows H alpha emission. There's molecules coming from these filaments, very, very strong molecular hydrogen emission. It has OH emission. Several molecules have been detected from these filaments. Very strong H2 emission. Very, very unusual by galactic standards. This is a fantastic challenge by someone with my skill set. So what I am is a old style spectroscopist. I enjoy thinking about how matter emits light and what you can do with the inverse problem with taking the light we saw and then deduce what happened out there from the spectrum that you see. These photons that come to us from across the universe last interacted with matter out there at very, very high redshift. The Siri does not understand, and I don't either. So
Interesting question.
Okay, this is, so you got two speakers for the price of one. So the very first spectroscopist, if you look at the spectrum, the optical spectrum of one of these filaments, you see something that does not happen in the galaxy. Now, so many of these strong lines are the standard strong lines, but the attention should be drawn is this nitrogen 1 emission, which is impossible to form in shock heating or photoionization. So he wrote several papers. I'm not going to go into the details about that, but you can't make this line in the galaxy. The only other place in the galaxy where you see that line this strong is in the Crab Nebula. And the Crab Nebula is something like these filaments. In the Crab Nebula, you have a pulsar wind nebula with synchrotron emitting electrons. And then you have the tentacles, the fine tentacles of the crab itself. It gave it its name. And these are very dust rich and they're very molecule rich. So in both these environments, the commonality is you have thin filaments. That suggests magnetic fields of some kind of instability. You have molecular gas with lots of dust surrounded by relativistic or 10 to the 7th degree plasma. And so that's a challenge even to imagine how you can do that. So this emission line is, this nitrogen 1 emission line is none of the above. It doesn't form in photoionized environments. Probably what's going on in the crab is also going on here.
We have a question.
Sure.
Ryan, you want to go ahead?
Yeah, so this is probably a remedial question, but so you're seeing these lines in emission. So what's the light that's getting reprocessed that's leading to the emission that you see?
There's two scenarios. The question is what,
Repeat the-
yeah, what the question in photoionization, you take a stellar continuum, stellar SED, and energize the cloud, the ionizing radiation fluoresces and is converted into different emission lines. So that's one way of making lines. The other way is by some kind of mechanical heating, by shock heating. None of the above is happening here. There's no light source very close to these filaments. And we know exactly what a shock looks like. This doesn't look like that. There are two different models that I'll describe as you go along. So there's the model of 10 years ago I developed on one sabbatical back at Cambridge. And that was using the hot surrounding plasma like a cosmic ray shower on the filaments. And what I'm going to talk about today is this decade's model. It may just be the cold end of the cooling flow. So we'll get through that. So it's a great question. So if it were like the galaxy, it'd be photoionization or collisionalization. So it's something I would argue is common to the Crab Nebula and this environment. So the first thing everybody is trained to do is you put your emission line spectrum that you can't figure out on a BPT diagram. So this is the original form of the BPT diagram with Jack Baldwin. And so the cluster spectrum is off here, off the top of the page. It's not on the BPT diagram. Lots of molecular emissions. This is a carbon monoxide line. Got lots of molecules in the cool core cluster filaments. And the first thing that shows you that this might be the case, the near infrared spectrum has the famous molecular hydrogen 2.121 micron line is very strong. It's nearly as strong as H alpha. And so this prodigious dust inventory, chemistry inventory. So you've got this hostile environment, which has managed, we think, probably to make dust, but certainly has made molecules. Okay, so the best observation, we had Spitzer observations of this region that Andy liked to call the horseshoe, and look very, very carefully at the lines. You have lots of molecular hydrogen lines and PAW features. Now, PAWs should be very, very fragile. They're benzene rings, right? They should be very, very fragile. And here in the middle of this 10 to the 6, 10 to the 7 degree plasma, you have these fragile features like molecular hydrogen. Some of this is the strongest molecular hydrogen line here, another molecular hydrogen line here. So these are some of the strongest lines in the spectrum. So that's another another mystery. So the cluster environments, you're trying to explain all this. You're trying to explain particularly the optical spectrum of the filaments and also the cluster itself in the context of an environment. So this is the same scale. Here is you can't quite see it. The quasar is right here. The filaments are around it, the filamentary system. And then this is the X-ray image. So you're down here in the core of this. So you have a very, very high pressure environment, far higher pressure than in the local interstellar medium, very, very hot. There are also relativistic particles because of the radio jets that are around here. And if you argue that there's kind of equipartition with the synchrotron emission, there's probably a magnetic field about 100 microgauss, something like that. But the pressure is a very high pressure environment by which we're used to in the interstellar medium. Yeah.
In the galaxy cluster, or at least in the BCG, like where does the magnetic field actually originate?
The origin of the first magnetic field is an unsolved problem. But yeah, where do the fields come from? Once you get the field, it's easy to keep it going. The original magnetic field we don't understand. In the general interstellar medium, there's an equipartition between the cosmic ray density, the MHD turbulence, kinetic energy, the thermal energy, dimension cosmic rays, and the magnetic field. They're in rough equipartition. But that's not thought to be fundamental physics. If you just build a closed box with different energies, and if you let the box kind of slosh around, eventually they will come into rough energy equipartition. So that field, it's like the minimum energy argument, the old Burbage minimum energy argument for synchrotron emission, that the least energy you can have is with this magnetic field, this density. So it's that kind of an argument. It's kind of a heuristic. It's not a measurement. There's the problem with making high finesse observations. I mean, you'd have to get 21 centimeter circular polarization to get magnetic fields, or Faraday rotation has been attempted. There's so many sources of light in this environment. It's challenging to isolate what you actually want. So I showed you one of the early images where you can see a silhouette of the infalling system. So Tom Cholin, and I think Dick Crutcher may have been on that, former colleague of yours. They did measure 21 centimeter absorption circular polarization. They got a line of sight magnetic field in that infalling component, but that's just thought to be a field galaxy that's along the way. So I don't know if a Faraday rotation's been attempted, but not successfully. Okay, so the original model we came up with for explaining all these molecules, and you have to make molecular hydrogen pretty warm to make it emit those lines that Spitzer saw. So these are rotational vibrationally excited molecular hydrogen lines. So those need a kinetic temperature of a couple thousand Kelvin to excite. That's why they're kind of unique and hard to do, because that temperature is almost hot enough to destroy molecular hydrogen. You need about 5,000 Kelvin to destroy molecular hydrogen. The rotation and vibration temperature you get from the existing observation is about 2,000 Kelvin. And so the initial thing we came up with 15 years ago now was to take the energetic particles in the neighborhood. So this is a public relations image of a cosmic ray shower occurring in the Earth's atmosphere. So when a very, very energetic particle, the cosmic ray, enters a cold atomic medium like our atmosphere, you end up with a shower of secondary electrons. It's something like a proportional counter. So the general rule of thumb for an astronomical plasma is you take the original energy of the incoming particle, and it's something like a proportional counter. It'll make the shower of particles that can barely ionize hydrogen. So you take this energy of the incoming cosmic ray, divide by 10 eV, and that's the number of shower particles that will come out. And so a shower of particles like that, what we showed in a series of papers we did back then is this can produce warm molecular gas, and it can produce that nitrogen 1 emission. So this is a weird excitation process, but something that can happen in nature. So that was a series of some papers about 15 years ago. So so let's fast forward to today and 1981. The original idea when the X-ray missions found that the X-ray spectra did not show 500,000 degree or million degree gas. And so you start out, let's say 510 to the 6, 5 million degrees, and start cooling down from the highest temperature. Should cool down 10 to the 6, 10 to the 5, 10 to the 4, 10 to the 3 down on down, cooling flow. And it would pass through temperatures of 10 to the 5 or a few times 10 to the 5, and it would make certain tracers. I'll show you some. And so that would be the cooler gas. That would be, if it's cooling and falling, it'd be towards the center. So the original idea, one original idea to explain this with a cooling flow was you put a screen of absorbing gas in front, an ionized screen of absorbing gas in front. So I promise not to talk about atomic physics, but bear me out. This is the only atomic physics you'll have to deal with. So this is the photon energy in electron volts. So visible light is off over here. The ionization potential of hydrogen is 13.6. And so this is an ionized gas, something like what you find in the intercluster medium. And what these curves show are various opacity sources, but what matters is the total opacity. So this is the cross-section, the ability of matter to absorb light. And so what you see out here in the X-rays, it's easy to absorb the X-rays. That's due to inner shells, let's say second row elements, carbon, nitrogen, that would be the K shell. You get up to the third rows, silicon, sulfur, those guys, it'd be the K and L shell are absorbing. So those are what they call the inner shells of a heavy element. And so it's the N equals 1 shell of a hydrogenic system, the N equals 2 shell. And so there's a lot of opacity out here. It means it's really easy for those inner shell electrons to block X-rays. But then when you get out to the UV optical IR, there's no opacity. And so you could be looking through basically what looks like a brick and absorbs all the X-rays in the X-rays. But then in the UV optical, there's no hint of anything in the way. And so the postulation in the early 1980s is you got to put gas of this kind of a property in front, and then it would prevent a view of the coolest end of the cooling flow, while in the optical UV, you'd see the entire thing, not know this is there at all. The community didn't much buy that. There are a few people at Cambridge did, and it sort of sat in the background cooking around for a while. And then the last sabbatical, Andy and I started looking back at this. So there's a series of 4 papers, Fabian et al., on the cooling, the hidden cooling cooling flow phenomenon. So the hidden cooling flow is the idea if there's gas with this property, which there must be, the hot ionized gas absorbs like this. You could see a geometry where this large opacity in the X-rays would block our view of the coldest regions of the flow while giving no hint in the UV optical that it was there. So what happened next was this code I've been working on, Cloudy, it does 1D magnetoroadiation hydrodynamics. And we've probably published a half dozen papers in that mode. It's painful converging an MHD model in 1D takes about a week when you carry the luggage Cloudy has on it, and you have to do it on only one core because of the nature of the problem. It's painful, but you can do that. And so this is a cooling flow done within the last year with Cloudy. So it has state-of-the-art atomic data. The reason this problem is so hard goes back to that many-body Schrödinger equation and the fact that atomic data is so messy. It's a very, very messy business. And that's a different conversation. So this is a cooling flow, where we allowed it to cool all the way down. And it's a cooling flow with a difference. Normally, when people plot this, they would plot flow parameters versus temperature. And you end up with a very sort of looks like a low mound. You can see everything. But it's important to remember that what's happening out there in the sky is it's cooling as a function of time. And the scenario is as a function of time. So this calculation follows a parcel of gas that starts out at 2 million, 3 million, 30 million Kelvin. And there's no heat source, and it's just allowed to cool down. So you can see in about 10 to 16 years, there's pi times 10 to the 7 years in a year. There's pi times 10 to the 7 seconds in a year. So this is about 1 billion years, something like that. Under 1 billion years, it cools down to a few million degrees, and then there's a very, very rapid, but not a catastrophic. It's a very well-resolved cooling down to very low temperatures. So there's no instabilities that occur along the way. Using today's atomic data is a very, very smooth cool down to, we followed it here to 1,000 Kelvin. And what's very clear here that you don't sense if you look at the way most people would plot this is that this cooling is very, very abrupt. Now, if you were to just, the challenge, you want to do a true 3D MHD calculation, and you want to have all the microphysics in cloudy. Well, cloudy can do 1D, 3 MHD. It takes only a week. If you're to do the proper MHD, radiation MHD, it would, that code doesn't exist. It would be very painful. So that's an aspiration. Someday you want to do the MHD right, and you want to do the microphysics right. That time is not right now. But what you can do, just as a heuristic, is you can assign kind of a speed to this. So this is time in seconds to figure out the scale over what this will happen. So if you take kind of the speed of sound for this hot gas as a typical flow speed, so you're talking about 50 or 100 kilometers per second. And then you take the time scale for this very, very rapid and abrupt cooling over that time. How far can the gas move? Well, guess what? It moves one of those filament widths. So I would bet you that those filaments are just a tail end of this cooling flow. But I can't prove it, but the numbers do work out. So what about this part of the cooling flow here? This is pretty hot gas. It should emit in the X-rays. And first of all, let's state what the cool core cluster phenomenon is. You've got the H-bombs in the center. You got this supermassive black hole with its jets. So it's squirting out relativistic particles in the jets. And what you've got to do is you've got to pick out this temperature here. And with those H-bombs going off in the center, you've got to keep the gas at this temperature, not any lower, because it would be a problem. You don't want to blow it to smithereens back up here. You want just with your H-bombs, you got to keep it right at this fine. It's a fine tuning problem. You've got to figure out some way to keep it right there. The hidden cooling flow idea is that there's extinction from gas that's blocking the view of this part of the flow. So that is not a new idea. That idea goes back 40 years almost, and it kind of was not accepted then. And JWST provides the perfect way to solve this problem. So this next figure is the JWST spectrum that you would see if you could see an actual cooling flow, cooling all the way down. And what we've done here is we stopped the flow at different temperatures. So in a computer, you can let it cool, then get to a certain temperature. Nope, no further. There's some reheating happening. So you can select out these different temperatures. The wave, this is microns. Is this, okay, this is clipped. Yeah, this is wavelength in microns, and this is internal units to cloudy. And so you see different spectra. There's a lot of lines here. There's a lot of diagnostic potential if you could get JWST to actually detect the hot gas. So you'd want to do is find a piece of the cluster, no filaments or anything, but you just want to get a blank field where there's only hot gas, and then you get the spectrum. So there's 3 different spectra shown here for you can pick out where you want to stop the cooling from happening. And if you go to the other camera that's available, the same, there's iron 2 is here. If you let it cool all the way down, this becomes a prodigious source of iron 2 emission. So what we had last year for cycle 3, we had 2 Pathfinder projects that got time, not a lot of time, and there's a Pathfinder to see whether you can detect the hot gas at all. And if it's not there, then you're not going to detect it. And so these are, of course, from the JBST proposal. And we got the Pathfinder time. The first observation is being made more or less as we speak. And the second set in the different program, the second observation should be late summer. So this is a line ratio. This is part of this killer JBST application we submitted. And what's shown here is this is the temperature where you're going to stop the flow from cooling. This is only part of it. And this is a line ratio. You can pick out, there's literally hundreds of lines that JBST could work with if you really could detect the hot gas. We have flux estimates. The problem is there's other sources of light in this environment. There's a AGN there, there's starburst going on, lots of stuff going on. Well, this is a line ratio. It doesn't matter which line ratio. I chose lines of iron that were very close to each other. You used iron has a very rich spectrum. And if you choose iron and iron, then you don't care what the metallicity is. You don't care about the abundances. And so this is 1 order of magnitude. So you can see that using the what are called coronal lines in the JBST bandwidth, you can figure out pretty much exactly if the cooling flow stopped, exactly what temperature did it stop at. And then you can't claim hidden cooling flow because nothing gets hidden in the infrared. The infrared goes right through this. So unfortunately, I'm not going to be able to answer the question. I'm going to say we're hoping the JBST comes through and there's some hint of emission, and then we will submit a big JBST proposal next cycle when we know what the answer is. So just in a way of summarizing this has been a series of hidden cooling flow. I've been various flavors of second and third author on this, and this is really driven by Andy Fabian's lifetime interest in cooling flows. So it's fun to work with. The advantage of getting older, you have lifetime friends that you've been around one another for 40 or 50 years. So you're together. It's like a husband and wife, or one can complete the sentence of the other before they even begin to speak it. So it's great to have old friends. And then just as a final act of humility, what you have to do is, look at this and you have to, it's a wonderful thing that nature has done in front of us. Nature has provided us the clues to figure out what's going on. It comes down to some spectroscopic problems. You have to be able to do non-equilibrium spectroscopy. It's just this is almost, you could almost print this, go down to Kinko's, doesn't exist anymore, but try, and print it on a great big board and hang it on your living room wall as a work of art. It would almost work that way. So that's my take on hidden cooling flow and how to have fun with photons interacting with matter. So thank you very much.
Questions here?
Can you say a little bit more about how you plan to separate out the AGN contribution from so you
Well, it would be from the lines. The AGN, the question is, how do you figure out the AGN contribution from the cooling flow itself? Long ago, in the very beginning of this, people tried to use the AGN to power the cluster hot gas, and that doesn't work. The AGN isn't nearly powerful enough. So that was the first thing people checked, was what the AGN would do. And at face value, it is a quasar down there. It's making lots of light, and not nearly enough to power the entire cluster. So they were looking for other things. But the quasar spectrum, what you'd be worried about is a scattered spectrum. But then you can't pick out any part of this. It's not going to have, with any significant aperture, it's not going to have a galaxy in there somewhere. So here's the horseshoe. So we've focused on in a region where, sorry, we've looked at blanks, and the purpose of the JBST is look away from the filaments and look in blank sky. So in AGN by itself, you could take AGN templates from the first generation JBST spectra, so we know what an AGN looks like. The worry, of course, is there are a lot of galaxies in the field here. You should have the ram pressure stripping and no interstellar medium in these galaxies as they float through the cluster medium, but that kind of doesn't work. So you're going to have to kind of look at what is in front of you, look at the spectrum, sit down and look at it very hard. The line widths are one super important clue. Hitomi found that the lines, the X-ray lines in the hot gas are about 80 or 90 kilometers per second turbulence. And so the cluster of hot gas would have that width. AGN emission lines are very different. The fear would be starbursts because they would have narrow lines. So we haven't seen the spectrum yet. The first spectra were attained last week. So as we speak, they're in the process of emitting a grant. And we should have a look at the spectrum fairly soon, I would hope.
Brian, and then, Brian, you want to go?
Yeah, thanks for your talk. So, I guess a couple of questions. So one about so you mentioned you find all these molecules. It's a tough environment for them. So, what's the expectation for how long they should survive there?
Well, we don't get a vote in that. We can see what nature did, and then we can be very humble and try to figure it out. My answer to this is exactly the same thing as happened in the Crab Nebula. And in the Crab, I mean, we have, the pulsar wind nebula, you have filaments, you have dust, you can see the extinction, you can measure the dust properties, and you can measure the molecules. And that bad boy blew up in the last 1,000 years. It blown to smithereens, and so we have this very rich molecular inventory. And so Andy and I tried, very hard to get telescope time to look at crab filaments, and that was all unsuccessful. But it's still tempting. So someone who wants to answer that, that this happened in the last 800 years. The environment, the pressure in the crab filaments. So what are you going to say? So it must be, okay, for the filaments themselves, there's an old argument, they must be highly magnetized. Magnetic fields inhibit star formations. If you start sort of a Jeans collapse of a gas, flux freezing means that the gas and the field lines are well coupled. So as the gas is pulled together, the field lines are too. So if you make a parcel of gas half as big, the gas pressure goes up by a factor of 2 because of the number of particles. The magnetic field goes up by a factor of 2 because of flux freezing, pulling the lines together. And then the magnetic energy density, or the magnetic pressure, goes up as b squared over 8 pi. So what happens is the magnetic field goes up far faster than the gas pressure or the gravity. So the magnetic field, if it's present, will inhibit star formation and will also protect because of the gyro radius, charged particles will not get through the field lines and get into the core. So you just wave your hands and say, let's not neglect the magnetic field. It must be out there somewhere. And the 100 microgauss, which you get from energy equipartition arguments, which you can't really believe, but it's all you can do. That would be enough magnetic field to both confine the filaments, prevent star formation, and protect the molecular regions. But then you get back to the exact same problems you have at redshift 10. How do you make dust so fast? You look at the crab, it did it in 800 years. If the crab can do it in 800 years, it's no challenge for starbursts at redshift 10. But we don't understand where the dust comes from in the crab either. And so there's a lot of work to do. So we'd argue magnetic fields, but that's the last escape of any scoundrel. You just yell magnetic field.
May I?
After Paul. I know,
Sure, thank you.
that one.
I understand the geometry of the flow you're postulating here. The original cooling flow models were radial.
Yeah,
right?
that's exactly.
And since cloudy is 1D, presumably, with time, your parcel of gas is falling in.
Right.
These filaments are largely radial as well. And so maybe you just kind of address this, but what's different about what's happening to the flow inside the filament?
Okay, what you can see, there's a radio jet. It looks like the matter has been stretched out by a synchrotron jet. It's not shown here. But you can also see in the Chandra images, there's a little X-ray halo around this. I mean, I can do the microphysics state of the art. So nobody can argue with me about the microphysics. I can't do the MHD worth a darn, as you just said. And so what we're looking for is a proper calculation. And so what I can do is what I can do. And you can see the physics is kind of headed in that direction, but your point is well taken. You've got it going in this way, but you got sheets going 90 degrees to that. So if you look at the radio jets on this image, it's not, Andy has others that show it. There is an axis of symmetry this way. It's almost as if the radio jet has pushed the hot plasma aside.
Mm-hmm.
But okay.
Well, that's what you see with the LCM. Right?
Yeah.
But your JWST observation is going to be single field.
So we've got two different projects, and they're going to be blank fields.
Multiple fields.
Yeah.
Okay.
But it would have been better just one honking big field exposure to try to get deep on the lines.
Mm-hmm.
So we're going to see, it's only a pathfinder right now. And we can see what we can see, and then that will be a much stronger argument for a later cycle. And they want a lot of time.
Telemachus, you want to go?
Yes, thank you. The notion that magnetic fields inhibit star formation is a remnant of the 60s, actually. I had shown in the 70s that by the time the density becomes 1,000 particles per cubic centimeter, the ambipolar diffusion time drops down to 1.8 million years. That's what I call self-initiated fragmentation and star formation because of ambipolar diffusion. So that picture has actually changed radically since then. And we verified that with very detailed simulations that included both rotation and bipolar diffusion and the effects not only on the degree of ionization, but also the dynamical effects of grains. So the general statement that magnetic fields inhibit star formation is actually not correct. They help it through fragmentation.
Okay, thank you. I'll look for that paper.
Thank you. It's 1979 that started and continued through the years.
Thank you.
So the solution to the cooling flow problem is that this gas with different cooling temperatures actually is there. It's just that in the X-rays, it's difficult to detect them. But if you turn on JWST to look at those tracers, you might be able to see them. So, but what strikes me the most is that when you show that cooling curve, the temperature just drops, to zero, literally zero.
In time, it does in time. Yeah, that's because the cooling rate really gets up. When you have a lot of electrons, you get lots of lines and large cooling. When it's super hot, there's not too many bound electrons and there's not too many lines to cool.
Then my question is, if the temperature is really that low after, say, a billion years, does that mean that we will see galaxy clusters that doesn't emit X-ray at all?
No, most of the line sight, they're clear, and there's some where you do see the iron 17. I don't have the iron 17 spectrum, but it was. I'd say there's clearly a lot of things going on, and the tools at my disposal are quite imperfect. But you would have to come down up with a clear idea of the geometry, and that's going to become a multidisciplinary problem because you have to include the jets here, and the AGN is down here. It's overexposed in this image, and it's in a very high pressure environment. So there's a lot of things that are very strange. So I don't know how to answer your question, but we have to be humble in the face of what nature has done in front of us, and we just have to figure out what is going on. How did this light get made?
A question might be imposed. I mean, I just wondering, does that imply that there are some clusters that's well developed and it's cooled down sufficiently, and there's no hot gas at all?
There are some clusters where you see the iron 17 lines, which were the killer for cooling flow back in the 80s. And so there probably is more than one thing going on. Perseus is kind of the poster child for this. The problem is in the northern hemisphere, so you can't get the southern hemisphere telescopes. So Centaurus is the one you work on the southern hemisphere. So there's ALMA and other. Perseus is the closest and brightest. You can see it with a pair of binoculars. I remember it from being a graduate student at McDonald. It was an amazing sight. You would need a lot more data, but I guess the point of this series of papers and then why I got involved is I think it's an interesting question. Maybe it's time to reopen this. Maybe the JWST tells us that this magical reheating at exactly a third the temperature is occurring. But anytime you see a model that requires fine tuning, you got to wonder, is nature actually fine tune? Unless there's some hidden correlation, is nature actually going to fine tune parameters? Probably not. My hunch.
Thank you for the very nice talk. This is probably a naive question, but what Becker asked got me thinking. So these, clusters is an environment of galaxies. So do these cooling flows have any impacts on the galaxies in the environment?
Well, there's supposed to be a blast of star formation down deep. And Telemachus has pointed out magnetic fields don't inhibit star formation, but you find people who don't know as much are using magnetic fields to prevent star formation. The canonical wisdom, these are molecular clouds. And so molecular clouds in a galaxy have cycle times of a few million years. They form and dissipate with the star formation. And so the linger time, if you look at the velocity field, these things have been out there for hundreds of millions of years. And so if you take the canonical wisdom for the galaxy, you're not going to keep a molecular cloud alive for that long a time. And so you can write a very long list of all the puzzles this thing happens. And the right answer is to honor each of these puzzles and try to understand what is that's really going on.
So your argument
sorry.
And massive stars are being formed are not visible to us, but they're ionizing, they're making the H2.
No, in this scenario, that's just the lingering ionization from recombining gas. And it actually produces that strong nitrogen one line.
But where are the stars then?
Yeah, so you argue magnetic field, but I'm sure we're about to hear the Telemachus. I think I heard your voice. You'll explain.
No, Gary, no, I wanted to sharpen somewhat the previous statement. Magnetic fields do aid fragmentation, that's definite. And the fragmentation leads to, it was a prediction before what so-called cores were observed. They were predicted as a result of ambipolar diffusion. However, it's really gravity, right, that is responsible for the formation of stars. What the bottom line is on the role of magnetic fields is that they slow down what would otherwise be free fall into dynamical, but much longer, typically by a factor of 3 timescale. So in that sense, they oppose gravity, but they help gravity to lead to fragmentation with one stage, not hierarchical fragmentation into stellar mass objects, fragments, cores, whatever they might be called.
So anyway, the observational fact from the scale of the problem and from the radial velocity that you can measure for H alpha is these things have been out there for hundreds of millions of years. And that's a mystery.
Okay, let's thank.
Okay.